you have to take the final action in this week. So hopefully you're in good condition. Today is not just about listening a lecture. Moreover, it's about future step to gain more knowledge, improvement our knowledge about the future trend of technology. It's about looking into the future. So Dr. Mustafa will be present and explanation about this novel PV technology. For this, you are interested in renewable energy. I think this is cutting edge. So, ladies and gentlemen, let me continue to convey our speech in Indonesian language for a half. So, baik para hadirin yang saya hormati, jadi kita pahami bersama bahwa kegiatan kuliah tamu, khususnya guest lecture, international guest lecture, itu mensyaratkan untuk menyampaikan setiap informasinya menggunakan bahasa internasional. Oleh sebab itu, teman-teman sekalian, saya juga ingin memperkenalkan bahwa sebenarnya bahasa Indonesia juga termasuk dalam hal itu. Selanjutnya, tentu tidak hanya penyampaian terkait dengan bidang keahlian dari Dr. Mustafa yang sangat menarik. Beliau juga, insya Allah juga menyampaikan terkait pengalaman beliau studi di Jepang, khususnya di Saga University. Harapannya ini akan menjadi insight untuk kita semua, karena beliau juga dulu berkuliah di tempat yang sama dengan kita, yaitu di Universitas Negeri Malang, dan kemudian melanjutkan S2 dan S3 di Saga University. Dan besar harapannya informasi ini akan menjadi informasi yang sangat berguna untuk kita semua. But I'm still wondering what's the important to convey, to inform or part or besides of our plant engineering technology. Yang saya maksudkan adalah karena tema ini adalah spesifik. Kalau kita coba cek terkait dengan power plant engineering, namun tidak menutup kemungkinan juga hanya irisan-irisan yang nantinya kita bisa dapatkan. Karena jika kita menengok terkait dengan tren teknologi masa depan, itu tidak lagi hanya membahas tentang efektif dan efisien, namun juga green technology. Dan saya yakin kata-kata green technology ini sudah familiar di telinga kita saat ini. Mungkin jika saya jelaskan detail, ini akan membuang waktu. Mungkin kita ambil saja contoh yang agak jauh, yaitu dalam penerapan green technology, kemudian di mungkin teman-teman yang di TKO ada electric vehicle, kemudian tentu juga kedepannya tidak khayal jika ada istilah yang namanya green manufacture. Dan satu hal yang akan dibawakan oleh Dr. Mustafa adalah hal yang penting juga berkaitan dengan green technology, yaitu PV. Baik, para hadirin yang saya hormati, memang kita yakini bahwa bagian yang paling tidak menarik dari guest lecture itu adalah mendengarkan sambutan maupun pembukaan. Oleh sebab itu, kami tidak akan membuang waktu banyak. Mungkin cukup sekian apa yang bisa kami sampaikan. akhir kata, welcome again to Universitas Negeri Malang, Dr. Mustafa, dan kami berharap kegiatan ini dapat bermanfaat untuk kita semua. Saya akhiri. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Arya Kusumawardana, for the inspiring opening remark. We now proceed to the material presentation session. This session will be moderated by Mr. Misbahul Munir, STMT, and delivered by our distinguished speaker, Dr. Muhammad Mustafa, Minister of Engineering, PhD. To the moderator, please begin the session. I'm sorry for the moderator speaker to wait for the presentation as an appreciation for the knowledge and time that you shared with us. We kindly invite Mrs. Vice Dean, Mrs. Ani Nurhayati. Please welcome to the stage. Present the souvenir. The souvenir given is to express our gratitude to Dr. Muhammad Mustafa, Registered Engineering, PhD, for his willingness and dedications to be our speaker today. I return it back to the moderator. Please start the session.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Today, I am the guest, the moderator of of the guest lecture of Mr. Muhammad Mustafa, PhD from Saga University of Japan. Okay. In this session, we will begin the lecture from Mr. Mustafa, and then the second is question and answer, and the last is closing. So now I would like to present Mr. Muhammad Mustafa to deliver his lecture. Please welcome.
Well, thank you very much for the introduction. So, good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. The Honorable, the Vice Dean of the Faculty of Asia, Dr. Ani Nurmendayani, then also the head of the study program of the power plant study program, Mr. Arya. So first of all, I would like to say thank you very much for having me here this morning. And actually, I also appreciate all of you guys that is coming here this morning, and also the organization that organized this event this morning. Thank you very much. And I am so honored to be here. I am so excited to be here. I would like to share all of my knowledge. Then probably this morning, my lecture, I don't want to be a quite rigid one. I don't want to be, how to say, I don't want to be too much rigid. I just want to be more like discussion. So if you guys have any questions, if you guys have any concern or everything, so you can just like share your thought. You can just like raise your hand and can just ask, even like in the middle of presentation. So for me, it's fine. So I think we are going to make this environment more relaxed, more good for discussion. So I hope you guys can enjoy. And then I would like to ask the PowerPoint for my presentation. Okay, well, so actually it's been a long time I'm not coming back to this university because when I was an undergraduate student, I was also alumni of the university, and then it was a very, how to say, nostalgic feeling when I seen the my school end, and it feels like I was still new student. So anyway, before that, I think I cannot operate this one, so I think I'm gonna ask you to just. Right. So before I talk about all of the material here, so I would like to introduce myself. So my name is Muhammad Mustafa, and when I was in bachelor degree, so I drew my bachelor here in University of Malang, in the Bachelor of Arts in Electrical Engineering Application. And then I continue my master degree in Saga University, Japan. After that, I got also an offer for the PhD. So I got also the PhD from the same university, Saga University, and I'm now a researcher in Saga University of the Electronics Laboratory, and also an assistant professor there. So next. So this is some of my publications. So if you guys interested in my research, what I'm doing, what I'm working right now in Japan. So I recently published paper, which is the fourth one, which is like this month, 2025. So basically, I'm working in material science and also applied physics, quantum physics, and crystal engineering, photovoltaics, material science, material and crystal engineering also. And then, yeah, this is some of my papers, journal papers. And then next. And then also actually very grateful that I recognized by the some awards that is given by the Japanese Physics Society. And the very last one, so I got the Young Researcher Awards in the Japan Society of Applied Physics, and I was the chosen from the 300 student from the 3,300 presentation. So I was the only one international student, and I was the only one Indonesian right there. So next. Okay. What is actually, I would like to introduce the Saga University at first. Do you know where is Saga? Have you ever been to Saga? Is there anyone that haven't been to Saga before? No one. Okay, because it's not really famous actually. So, yeah, it is actually not like a big city or not like a town or like Tokyo, Kyoto, or somewhere else like metropolis and everything. But Saga is just a country, it's just a city that is a very quiet and a really good environment for studying. So actually, you can see this map of Japan. So that one is the Hokkaido, and this one is the Honshu, the middle one, and this one is the Kyushu. So the Saga is actually located in Kyushu, in south. So even if in south, the weather there is not tropical. So Saga is very special because of the wind from the Taiwan, China, something like that. So because of the geographical location, so Saga actually has a very perfect condition for subtropical weather. So we have also the spring, very good spring right there. We have a lot of sakura, and then also that one is snowing days. Snowing days on like 1 or 2, 3 days, and it's very perfect because the weather is actually not that cold. The lowest one is was like only -6, -8, something like that. It's not that like -25, -23. So it's just perfect. But the thing is, summer there is actually hotter than Indonesia. So I think if you guys experience the summer also in Japan, I think you guys know that summer in Japan is actually like 100 times hotter than in Indonesia because of the humidity. And then also we in the fall actually we have the biggest balloon festival, which is in Saga. So everyone from the 60 probably this year or 60 or 70 countries, they come to Saga for the balloon competition. And yeah, Saga actually is a beautiful city in Japan. Thanks. And next. So Saga University, we have several faculty for graduate school. I only mentioned about graduate school because I just got information because all of you guys here are almost finishing your undergraduate. So if you guys are interested in the continuing your master degree in Saga University, so we have the School of Teacher Education, we have the Regional Design and Economics. We also have medical science, health science, and of course science and engineering, and also the graduate school of the agriculture. So if you guys are interested in this university, so you can access the website through this barcode. You can just scan it and then scrolling around. So we have a lot of information. What is the research? What is the faculty? Whether it's like the laboratory that you are really interested to. And then, okay, before this, I would like to play the introduction of the video introduction of the Saga University. I think you guys can imagine what is Saga University look like. It was in YouTube, I think. Yeah. Okay, it's not ready yet. All right. Okay. Ready? Okay. Okay, take more time. Okay, take more time. Okay, before during their preparations, I would like also to say that it actually is a university for international students. We have several organizations and also events. Okay, it's already. I'm done. It's fine.
Halo. Halo. TV. Yeah.
So everyone here is from 4th year student or 3rd year student or 2nd year? Is there anyone from the third year student? Third year. Third year student. Okay, so you guys are doing your thesis, special thesis right now. Okay, this is actually a very, I would say, quite tough time for you guys because I've been there. So it's okay. So is anyone from already fourth year or fifth year? Nobody wants to say that. Oh, I'm fifth year because no, guys. Look, I was also graduated from university for about like 5 years because I did an exchange student also in Japan at that time, and then I had to terminate my study here for a year, and then after that going back here to finish my bachelor thesis. So I think the biggest type of you guys finish your thesis in like a very long way, it's like more than 4 years, it's actually totally okay. As long as you guys has a reason why you are doing that. So, yeah. If you don't have a reason, that's the problem. Okay.
Tata University is a national university in the heart of Kyushu, with three campuses: Hanju campus, Bandashima campus, and Narita campus. With around 7,000 students within 6 faculties and 6 graduate schools. Here in Hanju campus, we have 5 faculties and 5 graduate schools, as well as the library, cafeteria, and research center. It is close to the city center, providing easy access to all the needed amenities. The National campus is well known not only for a medical school, but also for a university hospital, and is committed to its standards of excellence and provides an outstanding training opportunity to the medical students. Arena campus is a former place of the Arena College of Ceramics, a leading school in ceramics education. So let's begin our tour in Hanju campus. And we are now on the Cypress Street. The Cypress Street is home for the Arts Museum, Organization for General Education, the Galileo Base, and the University Hall. In the University Hall, you can find shops, cafeteria, and a dining area surrounded by gardens.
On the library street, you can find the library. The Faculty of Agriculture, and the Catholic Hall.
Here's the Sakura Street. It's very popular among these students, especially in March when it is at its peak blossom. On the Sakura Street, you can find the sports center. The Faculty of Science and Engineering. An Opti Cafe.
Patrocina campus to specialize in medical education. Alina campus specialty is ceramics. Students can be creative and explore the unique history of ceramics in Alina.
So, international students have everything they need to enjoy a fantastic time in South University. Bye-bye.
Okay, thank you very much. So matane means like see you. It's not like matane. So like if you guys like you have a conversation with the Japanese and like okay let's see you tomorrow. You can just like matane with friends, and then also you can say jamata. Also you can say sayonara is actually not really saying because it's very how to say formal, but mata is like more how to say casual. So anyway, that's the introduction of Saga University, and then actually I know them all in the video. So the moderator is also my friend from Thailand, and she was the most beautiful one. So we choose her as the as a moderator at that time. And then yeah, actually we are arranging this kind of video. We make a lot of program because actually here also in the organization we have the Saga University International Student Association. And I was the president of the organization for 1 year in 2023. And then we have also the Indonesian student community, we call it PPI. And then we have also the university student clubs. And then we are arranging a lot of events and things. So if you guys are interested in studying in university, especially or other countries, I think you don't need to be worried that you will be alone or you will have no activities or groups and things. So you guys can join everything. Next. Okay, I want to also the introduction of the Department of Electrical and Electronics Engineering. So here, actually, we have several laboratories that you are interested in. I think you guys are in professional, you guys are in electrical engineering field also. So we have the microwave and milliwave circuit and antennas. So this one and that one, the high power, high frequency device for the wireless power transmission is in one laboratory. And then we have also designing and analog and digital circuits. And then we have also plasma electronics and advanced computational engineering. This one is doing programming and everything. And then we have power electronics. Power electronics means the electronics for power device. So in this laboratory, they are focusing on the growing on the diamond semiconductor. So they grow diamond in the lab and use it as power devices. And then we have also the electric discharge, and the last is the optoelectronics, which is in my laboratory. Next one. Okay, so the optoelectronics laboratory, here we have several research. I think you guys are not really familiar with this kind of research because it's actually in material science mostly, and the application is actually in the solar cell mostly, or LPG or something like that. So we have the zinc telluride oxide. So we are working on 2,6 material compound and also 3,5 natural compound. So we make the solar cell based on the new material. So in my case, we have the zinc telluride oxide radiated solar cell, and then we are also doing doping in the zinc telluride, and then also carbon telluride. We have also the quantum dots. And then we have also the doping in the zinc telluride. Also the photoelectrochemical oversplitting. I will explain this like briefly in the next slide because I think you guys have to know the basic of the this one. And then we also recently working on 3,5 compound in the gallium oxide. I think you guys know gallium oxide very well because it's a very famous material for the electronics devices. And then also in sputtering, I think here in Malang University we have the sputtering machine too. And there we are also doing the copper nitride and also the copper oxide. Okay, next. study and scholarship. I think this one is going to be very useful for you guys. So I think I want you guys to really listen to this one. So first of all, if you are interested in studying in Japan, I think I need to introduce you about the working lifestyle in Japan. So for the graduate student, for the master, actually we have in the learning and evaluation, we have the weekly meeting with the professors. So all of the laboratory in Japan, not only Saga University, we have the weekly meeting. So for the research updates, everything you do is reported every week. So in 1 week, if there is some laboratory that is quite strict, in 1 week they do like 2 times. But in my case, I do like only 1 times in the on Monday. So on that day, so we do like a discussion with the professor and then also other lab mates, and then also we do evaluation and then we do a planning too. And then after that, let's do that. Okay. So and also after the arranging, so we do the implementation. Of course, in our field, so especially in my field, so we are doing experiments. We are doing wet lab and things, example and things. And then after that discussion again, and archive means that whatever the result you get, so you will be published in, like, for example, conference or a journal paper. But for the master student, so you don't really need to make the journal paper, but you need to go to the conference, academic conference. And the last one is innovating, means like after you archive your data, so we try to do what is the next step that we can do. Okay, next. Well, this is a scholarship that's actually available in Saga University or in Japan, all of that. So the first one, I think you guys are really familiar with the Max scholarship. So I got Max scholarship for 5 years. So since I was master until I'm doing my PhD, so I got Max scholarship. So in Max scholarship, actually the benefit is the education fee, which means that all of the tuition fee, all of the university tuition fee is free. And then the transportation fee and passport fee means like you go to the Japan with the airplane, all the airplane, airlines, and everything transportation is covered by the Max. And then it's also the free charge of the exam and university fee. Like if the university has to do some exam on you for the selection, so you don't need to pay for anything if you are registering in US. And then the thing is like the living cost is around like 144K, which is right now probably like 16 million Indonesian rupiah, I think so, per month. So you get this amount for for renting the house, for paying your bills, and then for eating, for everything. I think this amount is actually enough for living in Saga. But if you guys are really interested in other university, for example, like Tokyo University or Osaka University, which is like in a very big city, I think this one is actually not really enough amount for living there. So you need to do some part-time job, or we can do, we say like kaito. So the part-time job in Japan is actually very casual and useful one that this university student do it. So everyone also can do that. But in Saga, this is more than enough. So yeah, because the housing, rental, bills, and everything is actually cheaper than compared with the Tokyo or like other big cities. And then actually in Max, so we have 2 different entrance, which is the embassy and then also the university. So the embassy means you go to the Japanese embassy for selection, for apply, for application, and after you get selected in the embassy, Japanese embassy, you choose the university. So that's the flow. But the thing is for the G2G or the embassy tracks, you have to compete with the student in all of Indonesia, like probably 1,000 of them. And the second one is the university recommendation, which is you choose the university, you contact the professor, and then you apply in the university for the Max, and then university will select you as a candidate for the Max, and university will put you in the government. So it's kind of like from the university first or from the embassy first, something like that. But the university is actually a little bit tricky or a little bit different. For me, I got the U2U on the university track because I have experience in the exchange student also, and then my professor is actually really interested in my research. Also, I'm really interested in the professor's research, so we have same interest. So that's why my supervisor gave me a recommendation to apply in university, and fortunately I got selected in university candidate because at that time it was only like 35 or 60 students that is applied, and then it was only chosen 2 or 3 students from that one, and then I was the chosen one at that time. So it is actually the competition is actually not as difficult as the embassy, because embassy should be thousands of the students from all Indonesia. So yeah, but also in a G2G or in embassy, I think it's the chance is higher. For example, like the university is only choose only 2 people or 3 people, but in the embassy they can choose like 100, 300, 100, 200, something like that. So I think the chance is also big. Okay, next. And then what is actually you need to prepare for pursuing a study in overseas, especially in Japan. First is actually all of the graduate program right there is in English. So you don't need to be worried because you are not doing undergraduate right there. If you are doing undergraduate, you need to learn Japanese. But for the graduate, all of the programs are in English. So you only need to go. And then actually Japan is actually accepting ITP, so that's actually very nice chance. And then either ITP or IELTS, and then you can also use the Japanese language proficiency test. This one is actually very rare case. But the thing is that all of the program is in English, so you don't need to worry about that. And then the second one is actually research. But for the master, I think you don't really need to put a very detailed research on your plan. But the thing is that you need to know what is your specialty. You need to know what is your professor fields and everything. So you will be going in the right place. That's the thing. And then the third one is the supporting documents, means the recommendation letter or interesting motivation letter. So if you guys can provide these 3, I think you guys are being a good candidate for pursuing your next graduate degree in Japan. Okay, next. So this one is the introduction of my research field. Next one. Okay. Because you guys are really not familiar with what I'm doing, so actually my field is mostly in quantum mechanics or physics, or we can say quantum physics. So in quantum physics or quantum mechanics, we are actually there is a really famous experiment called Schrödinger cats. Anyone knows what is actually Schrödinger cats? Actually, I bring several merchandise from Japan. So if you guys know how to answer this, or if you guys want to answer this, I will give it to you. So this is a chopstick that has a very good pattern in like Japanese pattern. Okay, I think everyone needs to be more active. Don't be afraid. I think you can just say if you don't know English, you can mix it with Japanese. You can mix it with Indonesian. So if you can speak Japanese, it's also okay because I can speak Japanese too. Okay, if anyone knows what is actually Schrödinger experiments? No one knows? Okay, great. What is that?
Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, nama saya Budi Tiara Wulansari, bisa dipanggil Tiara. Izin bertanya, apa aja yang perlu dipersiapkan supaya bisa keterima kerja ke Jepang? Sekolah sambil kerja juga. Ya, makasih. Assalamualaikum warahmatullahi wabarakatuh.
Okay, I think there will be some misunderstanding here. I was asking about can you explain what is actually Schrodinger paths means? But it's okay. It's okay. I will appreciate your questions. How to be able to work and also study. Kuliah sambil kerja, work and also study in Japan. So it's very possible to do work and then also study in Japan. But the thing is like, which one is your priority? Work itself or the study itself? But I think the best way to do that is you need to go for the study first, and after that, during your study, you can do a part-time job or working. Because actually in Japan, so there is like several websites that is offer you the part-time job. Should I talk in actually Indonesian? But I don't know. But you guys need to keep up with the with what I say. So in Japan, so they have several websites that is over you the part-time job opportunity, and then it's a very easy one to apply, and then it's very it's not like a very hard or like you need just to apply and then go interview and then you will get a part-time job chance. So that's all. There's nothing else. So I think it's very easy. And then first one is the thing is you need to pursue your study at first because this one is the most difficult one. Let's say several conditions. First, you get the scholarship. You try the scholarship first, and then if you didn't get the scholarship, you can try another scholarship, which is I say there is also other scholarship like Rotary, like partial scholarship, and then others. And then the third one, which is the worst case, is you need to apply for the from your own pocket. Means you need to give your own money, and then after that, after arriving there, you probably can also apply for central scholarship. That's the three cases that you can do. And after that, after arriving there, so you can go for a part-time job. So it's a very good, how to say, planning for doing how to do like how to work and how to doing personal study. And I think that's all my answer. I think do you understand? Jadi kalau mau study di sana, so study dulu, baru nanti di sana mencari part-time job. That's I think the summary of my thoughts. I will still ask you: is there anyone here knows?
Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, nama saya Ahmad Daman atau bisa dipanggil Tata. Jadi eksperimen kucing Schrodinger itu kalau tidak salah adalah eksperimen di mana kucing dimasukkan ke dalam sebuah kotak, setelah itu di dalam kotak dimasukkan seperti sebuah gas, dan jadi kucingnya itu bisa dianggap hidup dan mati.
Okay, that's a very good answer. Actually, it's very good answer. Next one. Next. Okay, in Schrodinger cats, they put two cats in two different boxes, and they put a 50%. They put a radioactive here, like you can see, like the dangerous thing inside the box, and it gives the chance for the cats to be die or alive 50%. So they can die or they can alive with this one, with the radioactive. Next one. The next. Okay, so the first box, when we open the first box, so the cat dies. Because the possibility is either probably the cat's alive or the cat's die. But when we open the first box, the cat's die. And then what's happening with the second box? The radioactive has a chance for like die or not die. What is happening in the second box? Next one. That's dead or alive? No. The next one. It's either it's in a stage of dead and alive. Because we cannot open the box yet. So that's quantum mechanics. So we cannot discover what is inside the quantum mechanics. What is actually quantum mechanics is. We know that in quantum mechanics, wave and particle are at the same stage. So the thing is, before we open the cat's box, we know that the cat is in one condition, which is dead and alive. That's actually the very interesting thing from Schrodinger experiments. So this kind of the way to think is actually very actually difficult to understand because the quantum mechanics is kind of hard to this kind of point of view to understand that. So okay, next one. Well, I will go a little bit heavy material or heavy lecture this time. So I think if you need to, how to say, if you need to have some, question or things, so you can just raise your hand because it's going to be quite heavy for you guys. I know because I graduated also from this university because we don't actually have this strong basic in the material. So, but if you, is it my English okay? I mean, the tempo is okay? It's okay, right? Yes, I understand. Next. Okay, this is the background. Next. Next. Okay, that's all. So actually, I will give you a very brief, very brief basic things. We can just to make our point of view the same. So solar cell is actually a semiconductor diode that can absorb photons and then also convert it into electrical current. And that's very simple. I think everyone here knows. But my question is right now, because you are a university student, what is actually sunlight? It's not the stove. What is actually sunlight? Apa itu cahaya? Matahari. Who knows? What is actually sunlight? Sunlight cannot pass through this wall, but sunlight can pass through the object. Thank you.
Jadi pengetahuan saya itu cahaya matahari adalah sebuah gelombang yang bisa jika dilihat akan berbentuk seperti gelombang, namun jika tidak dilihat akan beraturan.
Thank you, very great answer. Is there another opinion? Is there another opinion? I want to hear something from faculty of vocation. Come on, guys. Is there another opinion? I want another opinion, another point of view. Nobody? Really? No one? Okay, deal or no deal? Okay, so thank you very much for the answer. What is actually sunlight? All of the scientists in this world do not know what is actually sunlight. So nobody knows actually what is sunlight. You cannot touch the sunlight. You cannot, see clearly what is sunlight. They can pass through the glasses, but they cannot pass through this one. They can, convert it into electrical current. So what is actually sunlight? What is that? What is energy? Where does the energy come from? The scientists don't know until now. Until now, they don't know. They just know what is sunlight because they know the effect what sunlight can do. So what is the sunlight real is that the particles that coming along this room or this there's no such theory like that. But the thing is that they know the effect what is sunlight can do. So So they can divide. Okay, sunlight is the package of the photons, and also they have the wavelengths, the stage, photon and the wavelength, particle and the wavelength, stage, something like that. They can divide it because of the experiments. But they actually don't know. We actually don't know. It's still in the box. That's why I call it the cat is either dead and alive. So you don't know inside what is inside sunlight. But the thing is, we can do an experiment on sunlight, and we know the effect of sunlight. Okay, that's actually a very brief introduction because I feel really how to say it, shocked, or I feel really like you know feel really wonder. The first time I go to class in master, I got the optoelectronics class, and then one of the professor come from China, and then he was coming from the room, and he was like, "Okay, everyone, do you know what is sunlight is?" He was like, and everyone was like, "Okay, sunlight is the photons and blah blah blah." Oh, that's an elementary school student who said like that. What is sunlight? And we all don't know sunlight, and he said, "No one, no scientist in this world know actually sunlight." We were like, okay, that's actually a really big mystery right now. Right, well, just a brief explanation next. Okay, that's solar cell. So what is actually the necessary of the renewable energy? I think you guys here are, enrolling in some renewable energy courses also. And then, okay, this is the net zero in 2016. The net zero means that we need to balancing between the energy and also the exhaust or the net zero, the CO2. But the thing is like if you see the net zero means like the red one, it should be decreasing. We should decrease that to save this planet. But the fact is in the blue one, so it keeps increasing. The emission is keep increasing. So that's actually very dangerous for this life. So that's why I'm really into the research in renewable energy because of this urgency. And then because of also we need to open our eyes right now. I think also in the disaster in Indonesia and everything is also because of the exploitation of the fuel. And we need a better solution. We need better things to do that. But let's not talk about government. But the things that we can do right now. So okay, so in renewable energy growth of the renewable energy, so it's actually quite good if you see the orange one. So actually keeps increasing. When it's like net zero, it should be like this big. But the current one is actually growing, but it's not that. So that's actually quite a problem. But the thing is that for the oil, it's still decreasing, but for the gas, it's actually quite similar. And the good news is also for the coal, it's also decreasing. I think because of the some of the countries they are using nuclear also. So, yeah, that's also becoming a concern. Okay, next. Well, solar cells. Let's make it more advanced. So if I ask you about basic solar cell, now I'm showing you the most famous figure of how solar cell divided. If you see the first, the first generation, which is in orange one, it can cost a very high, but it's lower efficiency. So in that group is the silicon solar cell, which is we see everywhere right now, in the road, in everywhere, in our plant, everywhere is in the first, first group. So the efficiency is like around 25%, 30%, something like that. So the highest one was like 35%. I was in United States of America. I was in California to attend some conference right there, and then some of the university from the UC Berkeley and then also Stanford, and then also some of the renewable energy laboratory in America, they try to also more improve in silicon solar cell, and then they can achieve like 35 or 36% in a very stable state. but it's not a commercial yet. So the second one right now, the second one here is the thin film. The thin film, the production is cost low, but the thing is the efficiency is much lower than the first generation. So in the case of the cost, it's actually very good, but this kind of efficiency is not really good. Then it's coming up with the third one. Third one is like low cost and high efficiency. But the thing is the third one, the only practical solar cell that exists right now is the perovskite solar cell. In the third one, actually there are a lot of kind of solar cell. For example, like intermediate band solar cell, which is I work on that, and then also the SSC, if you ever heard about that, and then also perovskite or perovskite tandem solar cell. So they have also in the stage of this third generation. But perovskite can do like 40%, 50% of efficiency, but the stability is very low. It's like when you do your perovskite and when you test it in first hour, it will be like great, and the second hour will be like down because of the like it's built from the organic materials. So I think they're all I think all of the perovskite people in this world are facing the same problem. Even when I talk with some professor in Stanford, some of the professor in the US, for example, the UK, so the problem is still the same. And also another kind of solar cell which is I work is the intermediate band solar cell. So this is actually intermediate band solar cell. Next. So here I would like to introduce you what is actually the intermediate solar cell. Here I have the range of the wavelength of the solar wavelength. It comes from 280 nanometer to 2480. And then you can see that the silicon actually, silicon can absorb only this range. Only this range. Because the silicon has the 1.1 electric voltage band gap, and it is converted to the wavelength 500 something. So the rest of the wavelength is just lost because of the band gap is not given. But in that case, in the intermediate band gap, we try to put another additional band gap in the middle. So the thing is the solar wavelength that has a very long silicon or also longer than that can absorb in the first band. The solar wavelength that has the middle wavelength can absorb to the band too, and then the short wavelength from the band to the band. So the thing is we can absorb almost all of the wavelength. Next one. I will give you a very brief imaging. So if you here I have the stand, and here I have the filter. So let's say this filter is the solar cell. So the stand is actually contains of like big stand, small stand, middle stand. If the filter is big, so the thing is like the small one cannot be absorbed. The small one cannot be catched. Next one. And then we try to do more. We add more like smaller filter, and then kind of like the middle one is actually catched. Still, the filter or the small one is lost. And that's why there's also additional small thing. Okay, so we hope that with this one, so the efficiencies can be increased. Next one. From here, is everyone like okay? I know the application, but it's actually the intermediate band solar cell. Okay, there's no question. So okay, next. Yes. Okay, this is actually too much. But the thing is that one of the material that is a good candidate for the intermediate solution is the zinc telluride oxide. Now, actually, a very tricky question. You can Google it, but I have only one chance. So, who knows the band gap of the zinc telluride? Band gap of the zinc telluride. One chance. The band gap of the zinc telluride. Zinc telluride band gap. Okay, raise your hand quickly. Raise your hand. Quickly raise your hand. Come on. The band gap of the zinc. This is very easy. Very easy. A very easy question. No one? No one on this one? This is not interesting? Okay. So, sorry, this is not interesting enough for you to raise your hand and answer the question. Okay. No one? No one? No one? 1, 2, 3, 4, 5, 6. Okay, you guys are so stand up. Oh, guys. Okay. No one? Band gap of the zinc telluride. If you get it wrong, so it's fine. If you get it wrong, so it's okay. Someone in the back.
So the answer is 2.26.
Correct. Can you take this one to? I'll have to. Okay, 2.26. That's a very excellent answer. So the band gap of the zinc telluride is actually 2.26 electron volt in a room temperature, and it's actually very big one. Like it's really very bad semiconductor. So if we do with the silicon is only 1.1 electron volt. So the zinc telluride actually has the wider, and then it can only absorb the shorter wavelength. Then actually, a very special thing in zinc telluride, if we introduce the oxygen inside the zinc telluride, they will have another stage in the middle. It's like magnetic, like the if you know like the valence band and conduction band. So if you can see here, the valence band and conduction band, the first constant and conduction band is like under that, and then when we introduce the oxygen inside, and then it will add another stage in the middle, and then the conduction band is getting out. So we have 3 different energy gap right now. So it's 2.5, it's 1.7, it's 0.8. So the 3 different band gap now we have. So we can observe 3 different wavelengths of the solar spectrum. So that's the theory of the zinc telluride oxide based IBSG. And then actually in the IBSG, so the theoretical calculation is saying that the efficiency is more than 50%, so it can be like 60%. If we can actually implement that one in a real experiment one, it's going to be solving every energy problem in this world. Actually. But the thing is, it's just a theory. So from this paper published, I think it's probably like 20, 30 years or something like that. More than that, I think. So it's still in a very, very low efficiency, still in a very laboratory stage. In my case, in our laboratory, we try to convert the intermediate band source based on the zinc telluride oxide material. And then actually the structure is a very complicated here. Right here. So for so PN junction. I think you know PN junction. For the N type, so we are using zinc sulfide. For the P type, we are using zinc telluride. And then for the intermediate band, we are using zinc telluride oxide. But the window between the zinc telluride oxide and zinc sulfide right there is we are using undropped zinc telluride, which has a very high resistivity. And after developing a lot of structure in solar cell, a lot of things, a lot of experiments. So the thing is, a very important thing is to increase the conductivity of the zinc telluride. So we have been dropping some. So we drop the zinc telluride with the phosphorus to increase the conductivity. Okay, I think this from here is going to be quite difficult. Alright, okay, next. Are you okay? Okay, fine. Okay, probably I will just add a little bit Indonesian to probably make you more understand about this. So let's now talk about topik semiconductor. So jadi zinc right itu kalau didoping dengan grup 5 atau grup 5 ini, dia akan menjadi p-type dengan carrier concentration yang bisa di-reduce. So when you put the 5 group of elements of the table periodic in the zinc right, we can drop it and we can control the carrier concentration. But the thing is, what is actually from the 5 group that is like very good for doping in the zinc right? So there are several reports for nitrogen, phosphorus, arsenic, antimony, or other. So the thing is like, in our case, phosphorus is actually very good. But the thing is, do you know what is the? Okay, I will give you as a question. Phosphorus. What is the easiest way in our daily life? What is the stuff in our daily life that we can easily find the phosphorus? What is the thing? Like, tell me, like, something. Okay, it's containing phosphorus. Anybody knows? Okay, I will count. Like, it's very easy. Very, very easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cancel. All right. So if you know the match, so if you know the match, so that's content of the phosphorus, which means when you like put a small, even like small, like things to korek api, so they can like flame. So because phosphorus is very hard to control, very, very hard to control. It's very dangerous and very toxic. But phosphorus is actually a good candidate for the cancer. So we are trying several things to overcome this problem. Next. So we are trying to do with the compound material. So if phosphorus is not a pure phosphorus, for example, like zinc phosphide, indium phosphide, selenium phosphide, gallium phosphide. So it's still quite easy to handle that with the compound material. And then here I will. This is a very also very complicated one. So bagaimana sih sebenarnya Pak Mustafa membuat solar cell? Bagaimana sih Pak Mustafa sebenarnya how to membuat itu pakai apa sih Pak? How I can make it? So the growth method we call it the molecular green epitaxy. So this is actually probably I think you just heard this one. You never heard this one before. Just heard this one this morning. So actually in this chamber, this one. So we have a several, things right there. The inside of the chamber is actually a very, very low pressure until like 1 times 10 to the minus 8 Pascal. So it's nearly same with the space inside this one. And then after that, we have a several material that is evaporated from the down part. We have the zinc, telluride, we have everything actually. And then after we heat up the material and it's coming out to the chamber, they can grow in, they can stick to the substrate, and then very good for the MBE is we can grow a single crystal. Like when you are high school student, for example, you learn in chemical like this stuff is like 100, 200 index Miller acid, something like that, like in your I don't know how to say it in class already because yeah, to be honest, I asked several lecturers this. When I studied in English because I think my basic of this, all of the material is in English, so I think I'm so sorry if I'm saying it in Indonesian. It's not in the proper Indonesian academic way. So yeah, I'm so sorry for that. So well, Okay, let's after we heat up the material and then it stick on the substrate, so it can follow the substrate orientation like 100, 200, 101, etc. So it calls the epitaxy method. Next. Okay, this is the illustration that I can show you. So here we have the material inside, for example, like zinc on the room. So and then they are coming up in the substrate, and then in the substrate they stick out there in a arrangement of the substrate, like in a good arrangement of the substrate. So we can easily produce the single crystal using the holographic fashion. And you can see here, we can also monitor the growth using the reflection hydrogen electron diffraction. So it's that one. So we can monitor how it grows using the electron beam. And then, yeah, this kind of setting is actually quite amazing. So MBE is actually a very rare machine in the world. Even in Japan, I think it has only like 4 or 6 universities that has holographic machine. In Indonesia, MBE. I already searched it in Korean everywhere, like in Malaysia, but I don't have it because it's very expensive. So if you see the effusion cells, only the effusion cell, one cell, it's like probably satu sel itu harganya sekitar 300-400 juta. Only for one cell, not for the chamber and everything. So it's a very expensive tool actually. But things like you can grow single crystal, which is very easy for characterization for materials and everything. Next. So, okay, in my very recent research, I tried to grow the zinc telluride, as I said before, using the zinc phosphide as the source. Next. Okay, so I will just very brief introduce you this one because it's actually very complicated. So, actually, in zinc phosphide, so it's not easy to produce the phosphorus that we want. So we need to modify the things, modify the like the cells and everything that we can use. We can produce the P2. P2 is if you do like phosphorus, there are a lot of elements of phosphorus that we can actually do that. P1, P2, P3, and then for doping, we need to get P2. So by this step, P2 is actually can be produced. So this design and everything, we already published it in our last publication. And then next. Okay, so you don't really need to understand actually this one. So by this research, I got my undergrad awards. So it was the very first time we designed, self-designed the holographic fashion cell that can produce the P2 with a very low mass. Next. Okay. So using this kind of machine, we can grow this kind of sample. So like we can grow not only like one layer of sample, we can grow a lot of layers of sample, the sample that we want. So for example, this one. So I can grow the uncooked zinc telluride, I can grow the phosphorus zinc telluride. But in my research, I want to know how much is the phosphorus is actually containing inside the sample. So I grow like uncooked phosphorus phosphorus something like that. So I want to know how much is the phosphorus is inside my sample. Because it's very beneficial for the data is very beneficial. We call it how to measure this one. We call it the secondary ionized spectrometer. So using this device, there is a primary ion beam that is penetrated inside the film, and then they will knock out the electron inside the knock out particle inside the film inside this one, and then the mass or beratnya itu akan berbeda. Jadi berat phosphorus plus berat elemen yang lain atau berat yang elemen-elemen yang lain itu akan berbeda dengan primary ion beam ini. Dia akan map up dengan massa yang berbeda. Nah, massa yang berbeda ini akan didetek oleh detektor dan akan di counting seberapa banyak phosphorus yang ada di dalam.
Aku mungkin aja bisa kontrol.
Next.
Bang Kecil bisa kontrol.
Okay, in my case, so when I do like low phosphorus, middle phosphorus, high phosphorus, so I do the kind of sample, so I can see a very good controllability of the phosphorus like this, a very good controllability of phosphorus, and compare also with other growth, other things, so I can grow very good. Next one. Next one. The other one actually to confirm the characteristic of the film is actually also the photoluminescence spectroscopy. So by this one, by this machine, we can know the band gap of the material. And I said like how silicon 1.1 electron, how the zinc 2.26 electron voltage, how actually scientists know this because of this setting. So actually we have the sample and we have the laser. The laser can be adjusted, like the wavelength can be adjusted, and then simply just put the laser on the sample in the vacuum, so they can have the reflection, and then the detector is detecting the reflective illumination. So from that we will know, the band gap and it's actually very big, actually very complicated process. I think you don't really need to do it. So, I mean, like, it's very hard, it takes time to know. Next. And this is actually the sample of the result of the photoluminescence. You do know that in the left side, there is a peak, there is a confirmation on the peak inside, and there is no off stage inside the material. Okay, next. Next one. And also the last one. I promise you this is the last one. The last one is actually the whole effect. So using this one, you will know the carrier concentration inside the sample, the peak type, the N type. We are using this device. We call it Hall effect. Next one. Okay, so this is the example of the result of the Hall effect. So we will know the carrier concentration, we will know the mobility, and then also we will know the resistivity inside. Okay. Solar cell. The interesting part, I think. We are going to the very last research. Right? So I tried to do a real internet-based solar cell. Because I already made a really good thing on the phosphorus layer. So I wrote this very simple solar cell, only zinc-based substrate, and then also phosphorus zinc, and then also zinc, just a very, very simple one. So this one, this solar cell, is actually the highest efficiency that we can do. Is only like 13% because it's actually not purposely for the solar cell application. This one actually for the intermediate and solar cell. So I just wrote this one, and then I characterized the sample. Next one. Next. Okay, I think you guys are very familiar with the IV curves because you take the, I think you take the independent courses. Okay, so in my case, I can get the highest one that I can get for the efficiency of the zinc-based phosphorus is 3.7%. This is actually the highest one since the first reported in 10 years ago. 10 years ago, it was like only 2.5. So I got the highest experimentally reported efficiency of the zinc-based solar cell. Even when you said it's only 33.7%, but it's actually not for the application. It's very beneficial for the material science theory. And then the next one. I'm sorry. So using the good, using the good result for the phosphorus dot signal, right, I can get the 3 high score 3.7% efficiency, and then this one was appreciated by the Japan Society of Applied Physics, so that's why I got my very last awards because of I get the highest reported one on the signal. Okay, and this one, and this is the very last, very last, very last, I think. So right now, yeah, it's because very last episode. It's not like okay, this is very last episode. He's still talking. He's still okay, sorry about that. All right. This is the last thing that is actually happening in Japan. I want you to know that what is actually scientists right now doing, and also our laboratory is actually currently also doing this one. So we call it like photoelectrochemical. We are trying to separate the hydrogen and oxygen inside the water. I think you know it very well about this one because it's one of the, like used in Indonesia. Okay, ada apa namanya motor berbahan bakar air, they're using this one. Actually, they're using hydrogen inside the water for the fuel. But untuk menghasilkan hidrogen dari air ini, untuk memisahkan antara oksigen dan hidrogen dari air ini, itu perlu source yang lain. So, in this case, so for the chemical water splitting, we are using the solar cell as the source of the energy. So, actually, in many research and also in our laboratory, we are using the zinc and solar cell as the source in the PhD. So actually, it's a very simple one. So there is a light absorption here. So we have the solar cell, and the semiconductor electrode absorb the photons, generating except the electron voltages here. After that, there's a transition, and because of this must spirit and travel to the electrodes like this. And after that, there is the electrochemical reaction because we have the anode and we have the cathode. So it's a very simple one. So in the cathode, it's here. So we have the hydrogen that is generated. And here in the anode, we have the oxygen. It's actually very, we can find it very easily the equation how actually the hydrogen and oxygen is split. So using this one is actually very happily done in Japan. All of the professors, researchers in Japan are doing this because it's very promising. And then when we can do the hydrogen separation, we are not only getting the hydrogen, but we are also getting the oxygen, which is very good for the environment and things. This is just a very quick introduction of the what is actually happening. Okay, next one. I think this is the last one. I promise you. Well, okay. Thank you so much for your attention. I think. I want us to have a very good discussion. So, ask me anything you want to ask. You can ask about research papers or anything. You can ask about the study or about China. I hope we have a very good discussion today. So don't be afraid to ask questions. There's no problem. I can understand Indonesian and English. I understand also Javanese. Japanese, I can also understand, words and people. So that's no problem. So just ask. Thank you.
Okay, thank you for this full presentation. The next section is question and answer, maybe discussion. Okay. From the room, you can introduce yourself first, and then you can ask anything that you want to ask the speaker.
We have only left 4 chopsticks, so first 4 questions.
Okay. Please, any question?
Masang makin dengan kita sudah mulai dari yang makin
Terima kasih ya atas kesempatan. Kan saya lebih dari di sini mungkin pertanyaan saya bukan tentang penelitian tapi
tinggal di portfolio
ingin menanyakan cara kerja sistem panel surya energi. Di sini saya ada pertanyaan mengenai cara kerja panel surya, Pak. Untuk cara kerja panel surya sendiri itu sebenarnya menangkap cahaya atau menangkap panas. Soalnya dari yang ada penelitian tentang molekul-molekul yang ukurannya berbeda. Mungkin di situ bisa langsung dijelaskan sebenarnya cara kerja sel panel surya itu bagaimana? Mungkin seperti itu. Terima kasih.
I think I need someone from the panitia yang untuk memberikan ini. So, okay. Should I answer it in English or Indonesian? Indonesian is also okay. Oke, jadi apa yang ditanyakan? Oke, ya, sekali ada penjelasan. Apa yang ditanyakan maksudnya adalah bagaimana cara evaluasi. Oke, as I said before, kita nggak tahu fungsinya itu apa sebenarnya. That's all. Apakah itu menangkap, apa menjaring, apa menyerap, apa tidak tahu. We don't know actually how it works. But the thing is that the very first thing how solar cell happen is because of the photovoltaic effect. So, jadi ada yang namanya photovoltaic effect. I'm very bad at remembering years. Jadi ada tahun berapa saya lupa, 1900 something. Jadi ada scientist yang menemukan photovoltaic effect. Jadi photovoltaic effect adalah when you put the light in the semiconductor material. Jadi kalau ada semiconductor material, and then kamu and then dipaparkan ke sinar matahari, itu akan menghasilkan listrik atau menghasilkan tegangan. Kenapa? Karena in theory, jadi di semiconductor material they have a band gap. Mereka ada valence band, ada yang namanya valence band, ada conduction band. Nah, valence band dan conduction band ini jaraknya itu namanya band gap atau band gap energy. Silikon itu jaraknya itu 1,1 elektron volt. Nah, cahaya matahari itu SAC, cahaya matahari apakah yang besar-besar, apakah yang kecil-kecil. Cahaya matahari itu bisa menjadi gelombang, bisa juga menjadi api. At the same stage. As I said, this is actually very hard to understand, tapi tidak hanya gelombang, tapi matahari itu is also particle. So it's also a particle. So it is two stages in one thing, because we don't know actually what light is. So that's why kalau kan kita tahu kenapa kok tadi ada 1.1 itu bisa jadi berapa derajat energi itu bisa di-convert ke wavelength ya, itu dengan the thing is like kalau ada cahaya matahari yang energinya melebihi energi gap ini, itu akan membuat elektron yang ada di bawah knock it out, dan ada elektron di bawah untuk lepas dari stage-nya menuju ke atas atau leaving the hole inside, the hole here. Jadi kalau di sini ada elektron dan hole bonding, kemudian ada cahaya matahari masuk yang energinya melebihi dari energi gap ini, energi gap material ini, maka elektron bonding yang di sini akan knock out, akan terlepas, dan ini akan terus terlepas dan hole dan elektron itu akan accumulated in the two different place ya. Nah kalau kalian akan menghubungkan ini dengan kabel, itu nanti elektron dan holenya akan mengalir. So that's why it called it photovoltaic. Ya, nah, kalau pertanyaannya misalkan apa yang membuat elektron ini knock up, apa itu energi, apa itu gelombang? Ya, it's the sunlight, it's the energy of sunlight. Ya, apakah itu sudah menjawab?
Barang gue ya.
Okay, I don't know if you are satisfied with my answer, so I think I can show you saya bisa menunjukkan beberapa hasil saya ada di list of the solar cell misalnya. Jadi lebih bisa ya, satu hal yang harus kita tanamkan adalah bahwa cahaya matahari itu ada dua stage dalam satu waktu. Bisa jadi gelombang, bisa jadi api dalam satu waktu. Dan misalkan karena memang efeknya adalah dua-duanya itu ada efeknya. Kita nggak tahu sebelum ini dibuka, sebelum kita tahu black box ini dibuka, sebelum kita tahu black box itu dibuka, jadi kucing itu akan tetap dalam kondisi hidup dan mati. Tidak bisa. Any other question?
Mungkin sedikit apakah energi yang dihasilkan oleh lampu yang energinya hampir sama dengan matahari, misal, apakah itu dapat menggantikan matahari itu sendiri atau ada perbedaan antara sinar yang dihasilkan oleh lampu dan juga matahari?
Kalau tidak bisa, kita tidak akan bisa gimana caranya saya mengukur sampel saya? Apakah sampel itu sangat kecil ya, 5 kali 5 mm, nanti bisa 5 kali 5 mm, and it's very small, and then saya tidak jemur sampel saya di luar, and then no, it's not working like that. Jadi kita namanya solar simulator. Jadi di solar simulator itu kita memakai beberapa lampu yang kita bisa atur panjang gelombangnya. Jadi lampu atau laser itu bisa diatur panjang gelombangnya. Misalkan, aku mau yang sekian meter, aku mau sekian meter, itu bisa. Tapi the thing is, apakah itu berbeda dengan matahari? Of course itu berbeda karena lampu itu membutuhkan energi. Kalau matahari kan it's a free energy. So that's the thing. And then lampu yang memang bisa dibuat, lampu is consuming other energy. Apakah bisa dibuat untuk menggantikan itu? Ya, of course bisa. Of course bisa, kita bisa kasih lah satu lampu dengan settingan nuansa. Oke, itu bisa menggantikan. Apalagi kalau misalkan kalau di saya ya ada school, gitu ada SD, SMP, kami juga laboratory. Kita punya beberapa panel surya, terus kita punya solar simulator, terus kita dekatkan solar simulator itu dengan mobil, dan di situ ada mobil balap. Itu sebenarnya kayak dekatin dengan size. Very possible. But the thing is that the energy is not sustainable. It's two different things. It's two different houses. It's two different things that we talk about. Dan nggak ada urgensinya juga kalau kita mau mengganti sinar matahari dengan lampu. It should be consuming other energy.
Terima kasih Pak.
Any other question? I'm so excited. Okay. Ada pertanyaan. Apa sih? Ada pertanyaan. Tapi itu Pak di sana. Itu.
My name is Pras. I'm from experience.
So about the experience in Japan. So the first I went to Japan for the first time for the first time was the exchange student. So when I was the student, I was the third year student. So I went there for the exchange program. So I got the chance to scholarship for 1 year in Japan. And it was my very first time studying abroad in Japan. And then my very first time also was this kind of so, kenapa saya bilang ini pasti anak-anak bilang that's what I feel when the first time I came to this laboratory. But the thing is like tidak ada yang tidak mungkin selain dari mesinnya ternyata pasti jadi belajar pulau kota kalian nggak bilang but as long as kita bisa lihat dan ada, I think it's still very possible to learn. So, okay, pertama kali saya masuk ke situ dan saya ikut dari platform ini it was also second habit of the study is so totally different. So they are very, you know, Japanese, this kind of stuff. But actually, that's a process. So the first time, because I don't really know about this laboratory and I don't have a really strong basic in natural science, so I did a lot of work. I did a lot of studying. I can study like until 2 a.m. in the morning, 3 a.m. in the morning. This is a very honest thing that I can tell you. Because saya bisa kayak lembur jalan saya bisa. Jadi ketika yang lain saya dan yang lain selesai mengerjakan BK, misalkan saya mengerjakan tugas dari saya harus belajar lagi ikut mengejar pengetahuan saya. That's quite tough experience. Tapi that's just a part of the process. And after that, go back to just study Malang, and then purpose saya adalah satu I'm in education, that's why I'm SPD. And then dari sini harus ada pendidikan kredit, so we must take on start and saya sebenarnya mencari beberapa opsi beasiswa. Ini because I really also want to go to UK, scholarship, karena saya sudah dengan profesor, saya sudah study coba untuk apply ke kembali ke sana for master. Setelah pun saya master in the end my professor offered me to go to the PhD. Okay, your performance is great, so if you want to go to the PhD directly with the state scholarship, you know, it was like also quite tough decision for me, but I said yes because it's a scholarship. So nothing to lose with that. So yeah, that's waktu itu karena memang sebelumnya saya sudah punya pengalaman, jadi lebih cepat untuk adaptasi, belajar dan lain-lain itu lebih cepat. And then setelah saya lulus PhD, baru this year on September. And that before September, my professor also researching same laboratories and I say because I really keen and a lot of time to me right now, and then I get also results. But still, it doesn't mean that I did not want to but some of you like, okay, well, you don't want to do that. Like the things that I can do, I can share my knowledge. Kalau saya bisa share apa chance that jadi what I'm doing right now, ya saya suka sekali. country which has facility, everything. Di sana sangat settle, di sana health, public health, and everything is just totally okay. The problem for me, the biggest problem is the kenyamanan ritme tadi ya. Orang-orang sama dengan orang-orang Jepang, jadi it's not a very easy things for me. Mungkin struggle untuk kalian tahu Jepang saja dan pasti beda beda. Is it answering the question? Do you want any other details?
I think our kind of researchers and professor, professor and researcher.
Okay, professor and researcher. What do you want to know about professor and researcher?
What is professor on there?
Okay. What is about professor in? Yeah, there are actually a similar professor in university also. I mean, like actually the professor or researcher like that is actually how to say it's actually very similar with the I don't really catch up the question, but I think the question is going to be like bagaimana untuk reach professor. Okay. Okay. So yeah, okay. I know you're okay. Saya understand. I think untuk master, as I said, how to reach. Kalau kamu mau ke Jepang, and then kamu mau study di salah satu profesor itu bagaimana cara reachnya? Okay. Ada beberapa cara untuk reach profesor atau researcher aja. Yang pertama, for example, of course, everyone must make connection. Connection is actually very important things this thing we can do. So we can talk with me, or if you don't want to go to the company, you can talk with the vice dean, Nick, because she also knows some of the professor. That's the first thing. The second one is actually through the academic conference. Jadi kalau kalian punya waktu, kan bisa ke conference, and then kenalan dengan professor, that professor knows you. I think it's easier for you to go to the professor there if you know him first. And the third one, it's going to be can we work or not? Itu bisa bekerja atau enggak? Tapi the third one that most people do itu just kita mengunjungi website and then kepo, and then pasti di sana ada email dari profesor. Jadi bisa langsung email. Tapi I think this way is not worth that much. I think so because the professors do not know you, like you don't have idea about the process. Tapi bisa juga dicoba kalau memang kalian very interesting atau tapi for me I think relation atau maybe you can talk with some of the lecturer here if you want to go there. So you'll be introduced to the professor. Probably not only Saga University, but also the Kumamoto University, because this university actually has an OU with that. So I think it's also possible. Okay, it's okay. All right, thank you. Any other thing? I still have to chopstick. Okay. Sekali ya. Okay, saya sudah.
So let me introduce myself. My name is Priscilla Carolina, and I am a first year student of manufacturing engineering technology. I have a question, so I'd like to know more about the challenge you faced when you were studying here at this university. You were an art education student, right? And then when you continue your studies in Japan, you took up engineering. Aside from your interest in existing mysteries, particularly those discussed in the field of engineering, did you experience any difficulties in shifting your academic course? And then my next question is regarding social life. it's not uncommon for differences in the primary language to become an issue. Did you also experience this? If so, how did you overcome it and manage to socialize? Even though you are experiencing more problems in your learning rhythm, are you also experiencing more problems in your social life? Thank you.
Thank you so much. Thank you, Bob. Great questions. Great questions. So, the first thing is like I think you misunderstand me. Like, my bachelor degree is the Bachelor in Arts of Education in Electrical and Electronics Engineering. That's the English words for that in Indonesia. Pendidikan Teknik Elektro. So I think I don't know why there's the arts there, tapi ya memang kalau di converted to English itu ijazahnya adalah Bachelor of Arts in Education. So I'm still in engineering actually, tapi pendidikan teknik elektro. Jadi I have an education on that. So the thing is like when I do my master, it actually doesn't have really a cross major or something, but yeah, only like several because I also got the education, so it's not my basic is not as strong as someone from the pure engineering. So, but the thing is okay. I still have knowledge in engineering and everything, so it's fine. The challenge is only like my basic here is actually not really capable, not really, support that much about laboratory here of electronics. So that's the answer. I think that's okay. And then the next one, the next question is actually very interesting. How about the language barrier between me and Chile? So in Japan, for the graduate school, everything is in English. Semua program adalah dalam bahasa Inggris. Kalau untuk master dan doktoral, jadi kalian tidak perlu khawatir apakah ada problem di dalam kelas atau tidak karena programnya adalah dalam bahasa Inggris. So they should teach you in English. The thing is, Japanese people are not speaking English. That's the thing. Jadi orang Jepang itu tidak ngobrol bahasa Inggris dengan apa namanya? Dengan orang yang kalau untuk sosial, not in the class ya, tapi kalau untuk sosial mereka nggak terlalu ngobrol bahasa Inggris. So that's why I need the Japanese skill. And I had an experience in that situation a lot. The answer is a lot. So the first time I came to Japan, I only know arigato gozaimasu. I only know that. I didn't know at all, zero. And then even like my tutor, I have a tutor right there. And my tutor cannot speak English, so we are using Google Translate each other. That was a very hard time. But 1 year I do exchange student and I learn Japanese, and then I can speak Japanese, and then I'm the person who is quite not really extrovert, but I like talking with people, so I practice my Japanese a lot, and then I'm becoming quite good in conversation. And after that, yeah, like just a process. And then the thing is like this. So if you go to the country that is non-native speaker of English, this cannot happen. This kind of thing is happening. Everything. You go to probably Spain, probably France, probably other than China or Korea. I think this kind of language difference is going to be a problem. But the thing is that you can learn this, so don't be worried. And then you also have another Indonesian student right there, so that can help you a lot. You don't need to be worried about that. As long as your program is in English.
Yep.
Jadi selama program kamu dalam bahasa Inggris, social and everything still can be overcome. Tapi kalau program kamu dalam bahasa Inggris sana, misalkan program kamu master dalam bahasa Jepang, you're gonna die. So, because you will not understand everything. So pastikan yang harus kalian pastikan itu. If you want to be more, like easy and everything, go to the UK or go to America. Because I went there this year in San Francisco, California. So I visit the UC Berkeley and I visit Stanford. Yeah, the education in America is very good. Like American dream. So I know some professor, they're just talking, they're just sharing a lot of knowledge that they're going to get mind. That point of view is also very different with the Asian professor. But still, they have a different style of study. And the thing for the language, I think you go to America or UK, there will be no problem at all. Singapore, for example, yeah. So yeah, that's actually my answer. Thank you. Any other question? I think, is it okay? The answer is okay? Okay. Other question? No, I think, okay. I think I still have the last job working here.
Perkenalkan, nama saya Sudir dari teknologi rekayasa komunikasi. Hanya kalau saya tidak salah tangkap, riset dari Pak Mustafa itu terkait material kerja. Nah, apa sih kenapa Pak Mustafa itu tertarik untuk mengambil penelitian di materialnya? Dan mungkin adakah saran atau masukan buat kami jika kami ingin ikut riset juga terkait material kuliah?
Okay, it's a very, very great question. Very great question, actually. Yeah, I was thinking about this when I was, someone asked me this question, same question, when I was, when I had a conference somewhere in Japan, and then it was a Korean professor asking me that. So the thing is like, jadi, apa saya concern di material, yeah, we know that silicon is actually nowadays necessary. And silicon exploitation is like everywhere. Even like silicon. Yeah, the thing is, silicon is abundant, but it still has its limits. So if we are not starting using other material that more abundant, I think the problem will be the same. So kita melihat renewable energy, tapi kalau kita hanya mengandalkan satu material, I think it's it's not wise. Karena silicon itu karena sudah overall exploitation dan probably also politics in China you can find silicon things. Jadi itu tidak akan sustain. It doesn't sustain. Zinc doesn't right. It's a very abundant and no one actually doing physics with that right here. So okay, literally becoming our concern about that's a lot of stuff. Tapi juga kita punya sama ya dari oxide dan lain-lain itu juga sebagai alternatif untuk apa ya untuk overcome this problem biar tidak terlalu overexploited. Jadi seperti itu. It's very interesting material itu banyak sekali kombinasinya 2,6,3,5 nitride. We can explore anything and they have a really unique characteristic, really unique things that probably you will have the idea what should I use with this material. Jadi kalau kalian punya material apapun itu pasti nanti material ini bisa dipakai ini, material ini bisa dipakai ini, finally bisa dipakai ini loh. We are exploring. It's very interesting. That's why I decided doing this. I hope it's answering your question. Yeah? Okay. Answering your question, you still have
kami juga kami ingin melakukan.
So what is material that you are working on right now? Apa kalian ada riset tentang material atau enggak sekarang? Belum ada. Tapi kalian tertarik untuk riset material? Senang saya ya S2 di material. That's a very simple suggestion. I mean, that's the thing. Tapi menurut saya start untuk S2 itu tidak akan segera kalau kalian startnya di S3. Jadi kalau mau material ya harus S2 gitu. Ya, the foundation kalian itu juga strong di sana. Kalau apalagi kalau bisa S1 ya kan, it is a very good one ya. Kalau startingnya kalau okay, I decided to do material science, so just apply for master in compare when you are applying in PhD, it's very difficult for me. Okay. Any other question? Okay, ada lagi pertanyaan ini. I'm so happy ya, karena I think the faculty education they are very active. Thank you so much.
Baik, perkenalkan nama saya Mas Zaki Rahman dari program studi teknologi rekayasa otomotif. Di sini saya izin bertanya, mungkin sedikit keluar dari topik pembahasan tentang sel surya ini ya. Saya di sini lebih ingin bertanya ke baterai yang digunakan untuk menyimpan tenaga dari sel surya ini. Apakah sel surya ini dapat menggunakan segala jenis baterai dari mungkin jenis VRLA, Li-ion, lithium ferrofosfat, dikarenakan sepengetahuan saya dari karakteristik baterai tersebut, dari sekian banyaknya baterai itu berbeda-beda. Mungkin ada dari self discharge yang tinggi, mungkin dari penanganan yang harus begini, begitu. Dan mungkin untuk pertanyaan selanjutnya itu, apakah saya menyebutnya ini PLTS ya Pak ya, apakah PLTS ini bisa digunakan, diimplementasikan di Indonesia sehingga bisa menjadikan kemandirian energi, mungkin tidak bergantung kepada PLN lagi. Baik, terima kasih.
Okay, that's a very good question. Very good question, and it's quite a little bit hard to answer actually. So let's talk about battery. So kita berbicara tentang battery. I believe ya di UM ini ada salah satu lab, I think in this building with the Professor Ali Mulia. Beliau also researching some things, some material things. If you are really interested, I think his laboratory is also very good laboratory. Beliau di superkapasitor atau di baterai sebenarnya di around. Tapi kalau when we talk what is actually the suitable batteries for solar cell, of course it should be any batteries we can use, any batteries we can use actually. Okay. But ya sekarang kalau kita berbicara masalah solar ya solar cell yang ada di pasar, they are using lithium. Everyone knows about that. But the thing is about discharge and everything. To be honest, I'm not really into that research field ya. Tapi sepanjang yang saya tahu, ada salah satu laboratory di University, tapi tidak belong to the electrical engineering, tapi it's more like chemical. So ada beberapa yang develop new batteries also suitable for solar cell. Dan bahannya I forgot about the material, tapi ada salah satu baterai yang dia punya daya tampung yang lumayan besar, dan juga it's very coming from a very sustainable material. Kalau baterai yang paling cocok apa, itu pasti orang baterai yang tahu. Kalau saya in a solar cell, instill in a kita tidak membuat PLTS, tapi kalau saya lebih ke trying to make another kind of solar cell, tapi masih dalam skala lab. Kita tidak punya a very extra research yang ada. Oke, kita punya baterai juga, kita tidak ada itu. Ya, as far as I know, there's still a lot of development also in batteries. Mungkin saya tidak bisa, saya tidak bisa menjawab penuh dan exact itu, karena saya juga I don't really expert in the battery. So I hope this can be, the question can be still in your mind, and you will ask this question probably to the guest lecturer that giving the battery lecture. I think you still keep in mind on that, because I cannot answer it very well. And then the second one is the PLTS. Okay. Apakah PLTS itu bisa menggantikan energi di Indonesia? Sangat bisa. Solar structure in Indonesia is abundance energy. Tapi yang menjadi permasalahan adalah lahan. That's why solar itu PLTS itu adanya di Canada, Amerika. Even in Japan itu tidak sebanyak itu PLTS. Karena memang membutuhkan lahan yang sangat luas, etc. Tapi memang apakah bisa menggantikan produksi di Indonesia? Bisa. One thing that I want you to know that is actually very happening in Japan. Ada salah satu laboratory, we call it Ocean Thermal Energy Laboratory. Dan ini menurut saya sangat high potential di Indonesia untuk menggantikan energi. Jadi, Ocean Thermal Energy ini dia memanfaatkan the difference between the temperature or the surface of the sea and the below of the sea. Jadi perbedaan temperatur ini mereka manfaatkan untuk menggerakkan turbin dengan bantuan bahan kimia. And it's a very impressive one. So university has one big OTEC, Ocean Thermal Energy Laboratory, also in Kyushu ya. Dan I think di Indonesia itu karena lautannya sangat luas, I think the development of this research is very important. Mungkin di sini kalau ada yang dari mechanical or like more like mechanics things, you can just approach. I think you can just approach to the Ocean Thermal Energy. Dan tidak hanya tentang thermal energy, tapi lab di sana itu juga mengembangkan tentang wave energy. Jadi mereka menggerakkan turbin dari gelombang air laut. And I think in Indonesia, gelombang air laut is very abundant too. Dan it's very, karena lautan di Indonesia sangat luas, I think dengan memanfaatkan ocean energy dan juga wave energy, I think it's becoming very promising energy untuk sustaining the future energy in Indonesia. Not only solar cells, but solar cells, like the problem is doing that. That's answering your question. Okay, thank you. Another question? Another question again? Very, very good question.
This one.
Okay. My name is Faiz. I'm from Electronic System Engineering. As you know, in the area of presentation, we know you have received several awards related to this presentation. I will not ask about your research. I will ask about the general things. Like, so in your opinion, what factors make you think that can make you stand out? Was it the content or your delivery or something else? And you can explain what, if it's the content, what content did you bring in the presentation, or what style of delivery did you bring in the presentation? Thank you.
Thank you so much. Thank you for a very great question. I never think about this anyway, so, but yeah, I got this question not in a formal forum, but I got this question in like just in a discussion forum. But this is actually a very good question, very, very good question. What actually makes you stand out in delivering the research? I think the very first one is how you know the language. So the language is very important. It's not, okay, we are not native speaker in English, we are not a native speaker in English, and then the barrier will be always there. The thing is that your level in language, in one exact language, is giving you a vibes to, like, giving you a point of power to deliver your presentation, or to deliver your idea or something like that. So I think the first one is the language, and the second one is the public speaking. The thing is like, is there anyone here joining BEM or Himpunan or other? So I was joining the Himpunan. at that time. And then I learned a lot because I was not be able to do a very good public speaking at that time, but I learned a lot in the organization. And then also in Japan, I don't really stay as a like early student. No, I'm not that kind of person, but I do some organizations. So from that, I learned a lot how to talk with people, how to talk in public, how to talk, like how to deliver the words nicely. I think the public speaking, you need to really handle that. So the first is then the second is public speaking. Of course, if you want to get the award, it's the okay. It's like your research. So I think I was appreciated because my research. So I get a lot of achievement and things, a lot of the highest experimentally measure efficiency in single right. That's actually a very huge findings actually. And Japanese society of art physics appreciate me for that words. Of course, also supported by the way I present my research, the way my language and everything. So I think that's also supported. But the main one is my work. I have one actually a very interesting story that I want to tell you. How did I found this idea? How did I solve the idea of the highest experimentally efficiency in development? So I was really frustrated at that day because I didn't know the answer. Why my sample was not showing any, result. I only got like 1%, 1.5%. I don't know why it's not improving because I already did get a good result on phosphorus, but I still don't get a good result in the solar cell. I was really frustrated. I tried a lot of things, and one day, one night at 3 a.m., I was sleeping actually on the desk, and then I dreamed about this sample at that time. And then I have actually one sample that I want to throw away because it's not for the solar cell, it's just for another purpose. But in my dream, I dream about like I measuring that sample. And then when I woke up, I was like, okay, probably I should measure it. And then when I measure it, I found something. And I was like contacting my supervisor very early in the morning, like 8 or 9. Professor, I have something to say. And we have a discussion and they say that, oh yeah, the problem probably is this. And after we try, we have an idea, theory, and everything. So finally, it's 3.7%. That's actually very quite memorable thing. Just remember. I think the 3 points actually that's English, speaking.
Thank you for your great experience, stories, and explanation. Thank you so much. Right, any other question? I think we still have time. I don't know. Okay, I think enough for discussion and question and answer. Thank you for Mr. Hall. I hope this discussion useful for the participant. So, thank you very much for participation. And I want to close this session. Thank you very much. Okay. Give applause for Mr.
That's something.
Thank you to all moderator speakers for the valuable knowledge shared today. We hope this session encouraged us to become leaders who contribute positively to our nation and society. Before we come to our last agenda for this event, I would like to please to all of the participants to stand up and to Mr. Hanya and the moderator speaker to take a picture together with us. Untuk pesertanya bisa berdiri mungkin merapat dan bisa bersama dengan. Ini untuk yang di sebelah sini ada rapat di tengah, dari belakang sana mungkin bisa rapat ke tengah. Saya bergeser ke sebelah
ini masang yang di ini ke sini.
Yang di belakang mungkin bisa maju ke depan. Saya cek kalau 1, 2, 3 bisa dan 3. Terima kasih. 1, 2, 3. Terima kasih semuanya. We acknowledge the beneficial and applicable in our daily life. Thank you for sharing your experience with us, and we hope to have another opportunity to learn together. That concludes today's guest lecture. I would like to thank all participants who have taken time to attend this event. I, Anita Babis, as your master of ceremony, sincerely apologize for any mistakes in word or actions. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Oh iya, masih tak kawan.
Pas sudah ya, rumah kenapa ya?
Oh, pas 10. Streaming.